Yeah, so today's meeting is packed with a few important topics. I think we will have allocate specific time slots for each agenda items to make sure we make the most of our time together and cover everything. Yeah, feel free to add the topic you want to discuss in the doc. Um, okay, cool. And the meeting recordings will be shared with the participants afterwards for reference and follow up. Yeah, let's jump to today's agenda. Um, yeah, the first one is the multi-node inference implementation, including approaches like the Ray MPI and Kubernetes native solutions. Um, yeah, maybe I can give some background on this one. So, like two months ago, when we work on the distributed inference, we noticed different inference frameworks. They have their own distributed runtimes. For example, like VLLM currently use Ray to orchestrate the GPU workers, and the DeepSpeed MII and TensorRT, they actually use MPI for the orchestration. And right now, I think there's they require those pretty mature communicative packages to orchestrate the workloads. And some community users shows interest to orchestrate those frameworks directly on Kubernetes. And so using Kubernetes natively to orchestrate the workloads is option. And I do see some users, they like to use, for example, like Ray on Kubernetes and MPI on Kubernetes. So I think these agenda items we like to talk about, okay, what's the, uh, like as a user, like what do you need? Do you think like Ray and MPI is enough, or you like to run on Kubernetes natively? So what's the like the position of the Kubernetes native like orchestration solutions like leader worker set? Yeah. Any comments on this one?
I have a couple of comments. So I think we want to distinguish between two things. One is the framework that enables the distributed, computations, parallel, which is MPI Ray, and the mechanisms by which we want to deploy those frameworks. Uh, Basically, the Kubernetes API. I don't think that Kubernetes will want to dictate, for example, MPI is the winner or Ray is the winner, or even like a third, like pathways. We have pathways. I don't know if you've read about like Google's framework for distributed computing. I think we have a blog post on this from Jeff Dean, or pathways. Like you can use anything you want to describe how to do distributed computing and distributed communication, like the communication library, right? Now, what we, I think, want to be able to do is to provide an API where we're able to deploy all these frameworks in an abstract way. Just like deployment is able to deploy whether it's a web app container or any other like front end service or even a back end service. Same thing here. So what I would hope is to try to understand the requirements for deploying these frameworks. Like for example, MPI requires setting up a secret and shared, for example, like potentially like shared, I think, file system or file, like a host file, or a way for them to understand, like for the workers to know who's who, right? Like the network IDs. I think same thing with Ray, with Ray. Just my 2 cents here. I have a couple of follow-ups as well on this, but I just want to stop to see if
From an analogy perspective, is it like stateful sets, right? Like stateful sets are the underlying provide a set of guarantees, and then you can either use that at a low level which is you map your needs to the guarantees statically, or you build something higher level, which is more like dynamic management. Like you could argue operators are one way to dynamically manage stateful sets, like for stateful workloads. Another one is like you can put a control component in one of the pods and drive it. So I think like that pattern for me showed up for like Ray-serve. Like you could put the Ray-serve head node container in stateful set 0. And, you know, the stateful set is providing the basic, you know, rank index, and then the glue code along with the Ray head node would sit at that first and manage, you know, the detail not being aware of config. Like, is there a formal term? Like framework is overused. Like I know we always use that. I don't want to call like operators is very domain specific. I feel like there's a good word for what orchestration of inter-process communication would be. Do we just call it like IPC framework?
Distributed, not also like just make sure that it is.
Yeah. Distributed IPC.
The IPC is specific to kind of the local node communication, right?
Yeah.
Probably like a communicative like a package or
Yeah.
those currently I think those frameworks, no matter Ray or MPI usage, I noticed they are mainly for kind of for the workloads itself is mainly for the control plane communication. For example, it waits for the all the containers to be up, set the barriers, and once they are ready, they continue the steps. And the data plane traffic, actually, most of the frameworks now still use the Torch backends. So sorry, the Torch with Nico backend for the efficient like tensor sharing. So technically, there's like even more frameworks than I think traditional workloads like the Ray MPI. They are for some resource orchestration, and the backend they use the Nico, and the underneath they may use Kubernetes for the resource orchestration. So that's kind of the 3 layers I am aware of. Yeah.
I think set membership, or what would have, like in the distributed systems language, you would have called it like config, like managing config membership and splitting that from quorum membership was like the big, I would probably say is the most important distinction in the Kubernetes ecosystem. And the most important development was like people realized that config in a set can be distributed from the data plane component. So I think that matches a little bit what you're saying. Like there's resource management, there's a set membership or membership management, which has to couple to whatever the underlying primitives are, or it has to, you know, do dynamic stuff, and all the dynamic stuff is, you know, unreliable at some level. So you can generally rely on a lower level to provide some primitive. You have your set membership and resource management, I think, as you're saying, the resource layer usually involves also or the config layer, the config management layer also usually includes resource management, or not resource management, but like resource targeting, right? Like these sets of devices have access to this stuff. That's all handled out of scope, and then you have to take the inputs, form a set, and then you do a bunch of distributed communication. Like Nickel, you could argue the configuration that leads to Nickel in the container or the process being configured correctly is also part of that set membership or config membership, whatever we want to call it.
Yeah, identity and I think collective communication are the 2 main pillars of those runtimes.
I am noticing here, like we could probably this clarity, I think, is something that we as a group, we're going to naturally fit lower in the spectrum than some of the other broader working groups. But like if we have really crisp terminology for it, like I think that was a mistake with stateful sets, is that we actually designed stateful sets to manage the config, but we didn't define the terminology or the mindset that made that easy. And I think this is an opportunity to improve that, you know, this time around.
Yeah. So I'm thinking for the like the community users, what's the next step? Like I think even like improving stateful set is something we can do properly in mid or long term. But short term, is it good for some members just to share like how to run those distributed inference on existing like MPI or array orchestrations on Kubernetes? At least give some like examples. For example, run like a tensor parallelism array on Kubernetes or on Kubernetes using MPI operator, etc. Is that a like a short-term win for users who like to play with the multi-node inference?
I think so. I mean, we've been working on this for a few months now, and that's why we came up with the leader worker set API. We have strong evidence that it so far been able to represent Ray, MPI, and even SaxML, which is a legacy distributed or multi-host inference server from Google. And there is an upcoming one as well that is like Jetstream from Google that will support multi-host. And we'll be able to represent it using leader worker set. So what I would like to understand is what are the gaps in leader worker set that you see and not able to represent these workloads. We have been able to actually have an example for VLLM. I can mention it here. And it's now actually referenced from the VLLM project itself.
One thing that I was thinking about as you were saying this, Abdullah, I do think like leader worker set comes from our own particular set of biases. Like the philosophy we had going through it was we know that people with TPUs need to support multi-host very commonly. It wasn't quite as in demand for GPU at the time, but the idea would be, how do you just have a completely decoupled component that acts a little bit like stateful sets and stateful workloads, right? You can write an operator, you can orchestrate stateful sets, but leader worker set was that lowest level primitive that would hide the common problems across fairly static multi-host inference. So that was the philosophy that went into its design. Maybe we should also say, like, what are some other philosophies people have about how they're doing multi-host inference? Because we saw only our perspective in that direction.
And it might be useful to present what that perspective is. Like, I can post a graph. Should I post it here? Like, Yajin, if free to remove it.
That would be great. Yeah.
I just pasted this here. I can speak about it a little bit. So that is the main philosophy behind leader worker set. Like the top side is basically your normal single host or single node or like single pod, inference service, right? You have a pod per replica, and then you will just use deployment. There is no inter-process communication or collective communication because it's not distributed, right? And here, I'm even here, I'm representing Gray, using Gray as a as the underlying framework, but like in this case, it's just like a single Ray worker and Ray head. So you can represent them as two single containers, right, in a single pod. But there is no communication between the replicas of a deployment. So this is a single host deployment at the top level. Now, if we want to do multi-host deployment, the way that I'm like, at least we've been thinking about is that we need to agree on the terminology here, but each replica, and by replica here we mean a distributed multi-host replica, is on of itself like a Ray cluster that you need to set up, or an MPI group of pods, and like a group of pods with Ray with an MPI driver and a bunch of workers, or a ray head and a bunch of workers. And so here I'm like using TPU slice, but it's the same for multi-host GPU. So you've got a leader worker set that creates these replicas that we see here, and each replica is a group of pods with a single leader where we can it can have its own configuration, because sometimes you might need to run a different container, or even you might need to request different types of resources for the leader. That leader being, again, the MPI driver or the head, the ray head, and then a bunch of workers, identical workers, run collectively the distributed computing. But the point here that I want to emphasize is that, again, each replica here is a ray cluster, or an MPI job, or in SACS, I don't know if anybody used SACS before, it's a SACS cluster, right? And then you replicate it, like if you want to scale up or down. So I just wanted to present this perspective, or at least the way that we've been looking at distributed inference. I'm not sure
And
if
each
the model exists for others.
and one note here is another like the philosophical point here is that each replica is a single failure domain. So like if you lose one of the workers, it's losing the head or losing the worker is the same outcome. You can't proceed until you replace and then reset the full set. So that's another philosophical thing that like I think is important. So
Yeah, basically this is a group of pods that live together and die together. You provision them together. When you autoscale the whole set together or not. And we can discuss like how we do failures. Like if a pod dies, is it enough to just restart that pod and the whole group will be able to recover, or we need to restart all the pods? In MPI case, yes. And so we have that, as a configuration. For example, in leader worker set, if, for example, one pod fails in that group, we will just go ahead and recreate all the pods, because that's how MPI works. In pathways, for example, we don't really need that because pathway is able to recover. But in Ray, I think Ray is the same potentially. So we have that flexibility. It's like failure handling. And again, the point here is with this model, again, like we're not talking about specific frameworks. You can use this for MPI, for Ray, and I'm not sure what DeepSpeed uses, but I think it's MPI under the hood. So it's going to be the same.
Right. I have one question here. I think there's so to orchestrate such workloads on Kubernetes. To me, I feel there's two ways. One way is like what leader worker set does. It concentrates on the resource orchestration and abstract those like quorum setting, etc. At this layer. For rest of them, I think the application itself has enough flexibility to configure to what it looks expect to be. All right. So in that case, the leader worker set won't know all the like the details inside those like pods, etc. So that's the kind of the design trade-off. You do want some flexibility, but you probably won't know all the information from inside. And the other.
What are some examples of that? Just because I want to make sure that we understand what your examples might be. So like, do you have a concrete example of the kinds of info or the config?
Yeah. I think like the race example in leader worker set it is the example because people need to write a lot of like commands and specify, okay, for the leader pod you need to do something like for example start rehead, etc. Let's just raise the example. If we want to use ray auto scaling, like then how does it work with the leader worker set itself to orchestrate the pod to auto scale the pod resources?
Okay, so let me just see a line terminology. So in that example, you want Ray to orchestrate the pods, whereas in I think like if we're talking about philosophies, like the leader worker set, is receiving instructions to orchestrate slices of static pod replicas. Kind of what you're describing, I think, is a model where you want to create in a different orchestrator, or there is an existing orchestrator like Ray, and you want to use Ray to do that. So Ray is the orchestrator versus leader worker set, or because like leader worker set, then you could put it under Argo, you could put it under whatever. But if you wanted to lean into Ray, you would have a Ray. Is that an appropriate analogy?
Yes, I think there's two patterns. The first pattern is let's say the application drives the auto scaling, and the second option is the platform. They can send the acquisition or preemption information to the workloads, and workloads react to those signals. So those, I mean, like Ray auto scaling definitely, for Ray, choose the first one because Ray itself has the auto scaling. It's the actor auto scaling, and it drives the Ray node relate. Actually, it's a pod on Kubernetes, and the pod on Kubernetes actually drives the node level auto scaling, VM level. So that's there's a hierarchy. I mean, for my point was if we adopt such designs, I mean, lose the lose the designs. How do we want to make sure those features can support like easily? And that's I think that's the difference between like leader worker set and the Kubernetes, right? Kubernetes, it does some native designs around Rays and make sure Rays features can run pretty well on Kubernetes. But the thing is
pretty well, I think, is the trick, right? And we've had this discussion. So there's a broader discussion that I think we've had a lot of that we'd also like to have in the multi-host orchestration group, which is when you reach like, what do you want to recreate in Ray? Like what's essential to Ray that's better than what Kubernetes can offer? What's already in Kubernetes, and you've got to decide which side you want, like node auto scaling in Ray, node auto scaling in Kubernetes. And then there's the third one, which are things that can never be effectively done in Ray because, by putting the responsibility in Ray, it's competitive with, the things that, your primitives in Kubernetes want. So this is another philosophy, which would be, how do you think about the inference workloads? Are they independent and are they part of your Kubernetes system, or are they part of your Ray system? And then you're trying to map down the advantages and the constructs that Ray does better than Kubernetes. We've had that discussion. Maybe Abdullah or Jan, I think like this is a topic we want to dive on.
Yep.
Maybe like we just call that out as two philosophical trade-offs of the Ray way or the kube workload way, and then help talk about the next aspects.
Yeah, I think yeah, and Abdullah raised their hands. I forgot who raised first.
Jan first.
Yeah.
Yeah, it's a question for Abdullah, I think, or for anyone working on leader worker set. Since you mentioned the architecture and how to handle failures depending on the framework you are using, is there a way to specify the success and failure conditions, like similar to the MPI job?
Yeah. So right now we do have like a failure policy there, either, for example, recreate all or restart all on any failure. The other one is basically just restart the failed pod in place. You can choose depending, because that will depend on the framework, whether the framework will be able to handle it or not, right? Like what failure policy the framework requires.
Yeah, are there like use cases to specify more specific conditions that require information from each individual parts or replica set?
You mean like, for example, on container exit codes or something like that?
Yeah.
We don't have that yet, but it's an interesting extension. But there is, like, in general, there is that, like, failure policy API that we would be willing to, we want to extend depending on on what frameworks is able to handle. Definitely, we should do like the finer granularity that we can, right? Like if there's a framework that can handle failure by restarting just a single container based on a specific exit code, we should do that.
Yeah, I guess that's a possible use case. So it might be useful to expose those information for those success or failure policies to use.
Yeah. I wanna again follow up on Clayton and Jasmine. Like I think this is really important discussion. There are again like two ways of deploying these workloads as you folks discussed. One where you have you relinquish or control to the framework, and the other one is where we would like Kubernetes to do most of the heavy lifting. Plus, and the reason that you would want to have the other approach is it integrates better with the rest of your workloads, the rest of your tooling, and whatnot. So that's the LWS philosophy here, being kube native. Basically, HPA is doing the autoscaling, not the array autoscaler. Cluster autoscaler is doing the node auto provisioning or node provisioning and infra auto scaling. Metrics as well. It's something that integrates with the rest of your metrics, system. I don't see them as either or. I see them as two options. In my mind, the Kubernetes, again, quote unquote, native way is something that the platform engineer would probably most likely prefer because they don't want to learn about Ray. They just want to be, okay, I know Kubernetes, I handle Kubernetes, I know how Kubernetes work. I will just integrate whatever you want, whether it's single host or multi-host inference with the rest of my, tooling and ops. The other approach, which is like, you want to be utilize what Ray, for example, does, which means you need to learn two things: how Ray does autoscaling, even how Ray service works, and how it exposes the service, etc. The second one, I see it's valuable. It's not something that LWS targets, and it's not a design goal. KubeRay would address that for you, for sure, right? It creates the cluster, and everything lives inside the cluster. And what I see the main target audience for this is like the data scientist who's trying, to experiment and test and fine tune their service. But once you want to deploy it in production, I think it's a completely different ball game. That the first approach that's Kubernetes native would probably be the stickiest and most desirable.
Yeah, I mean, and this is actually I think this is like a great bias / perspective that we as a working group need to talk through is like, I think my bias has always been to make Kubernetes as good as possible as serving production workloads and reasonable to support at like most development workloads, right? It's about the workload sharing. It's about like thinking about workloads as needing primitives and then being able to put layers on top of them. One of the consequences of being good at putting layers on top, like operators or frameworks like Ray, is orchestration frameworks like Ray or Slurm, is then those are better at some things, but then it comes with trade-offs, right? Like resource sharing between Ray and other inference workloads or other GPU workloads is going to be painful. Some people, as Abdullah mentioned, have the use case that they might have multiple competing groups using different technologies. I think in those cases, the kube-centric way tends to win. Because what ends up happening, if you have different groups sharing resources and there's a team that's like, I want all those teams sharing resources, they're going to go say, well, do things that standardize how you share resources so that they work together. Now, over time, that tends to lead to the lower, but that doesn't mean that that's a better approach. It just means when you have lots of workloads with different needs, you want to put as much common elements in between them so you can efficiently share. On the other hand, like if you're doing all of your training and serving as a single team in an array cluster, all that kube stuff is basically just overhead. So I think within the remit of the serving working group, like even though this is mostly batch, one of the statements that maybe we want to make is like kube should be really awesome out of the box at serving inference workloads if they're going to be a huge enough percentage. it doesn't mean it will be the best at all kinds of inference workloads. So I think what you've hit on, Judgin, is like leader worker set has a dual, which is the framework down approach. Maybe two questions we want to ask are, how do we make sure that the framework down serving, ray-serve, other approaches that other orchestrators might come up with work well, and then maybe in other frameworks that platform teams want to build. And then the other question would be, what are the common pieces between something like a leader worker set and something that ray-serve needs? Because that, I think, is actually a great question, because you will hit pain points if you go far enough on one side or the other and then realize you want. So like, what's the middle ground between something like ray-serve and something like leader worker set? Is that something that we as a group look at? I think in my head, I would hope we could do something, but I think like leader worker set's very nice. It's a single primitive. It uses nothing except cube. You could duplicate it yourself in code in an operator. How can we make that easier? I think is kind of one of those questions as well. Like if somebody goes and makes Ray, the topology that Abdullah showed here, easier, does that make the Ray use case for ray-serve easier? We haven't talked about that question yet, but I think that's a natural one.
Yeah, I think that sounds good. I think coming back to my original like point, I think solutions like Kubernetes or leader worker set, they have different design principles, right? Like some tailors for some specific workflows, and to make sure most of the like framework specific features can be well supported. And leader worker set definitely choose a different way to make sure most of the inference solutions can be supported on this one. Yeah, I think I'm saying I think both ways sounds good to me. And I want to raise another point is since internally we invest the Ray a lot for distributed inference case, and technically we like to go with the way without Ray. We for example, we adopt a VLM for some smaller models. So we think that's to make it work on like multi-host, Ray is the kind of a blocker, because the Ray itself the workload used some minimum features from the Ray and more on the resource management side, and that can be replaced by Kubernetes easily. So we also work on those features, how to make sure inference frameworks itself get rid of the specific orchestration solutions and make sure they can work on Kubernetes directly, so they can bridge to leader worker set or other orchestration solutions. Yeah, so that's another direction. Yeah.
One of the advantages I think that we have is that most frameworks have to work on VMs. So I think and Abdullah has this came from this is created as one of Abdullah's internal docs about a topic like this, where we were like, most people can work from getting a static config, and serving is a lot simpler than stateful was. Like stateful, you can configure etcd with a static configuration. This approach actually for TPU slice, Red Hat went through a design effort where one of the first operators for you was the etcd operator. It was horrific, right? It was the first one. Nobody really had experience in what worked and didn't work in operators. Red Hat actually went through a technical evaluation of etcd configuration that looked like this, where you would have 0, 1, 2 pods in a stateful set, and 0 would do your config propagation, but it would always be static, and you could do reconfig. But the mindset there was, then you're not coupled to higher level failure domains. One of the worries I actually have, when you think about trade-offs between framework centric and whatever, is you need that higher level Ray to be independent of failures. That's one of the advantages. What are the one of Ray's core design tenets is that a lot of operations are delegated to the workers, not centralized in the control plane. So I actually think that's an advantage of Ray, is like Ray is kind of built with a lot of decentralization in mind. But as a consequence of that, like it still has a head node, but the workers make a lot of fast decisions. They don't have to do a round trip to the control plane. That comes with a security trade-off. So I think like if we were thinking about how we framed where we were going is you want serving workloads to have as few unexpected failure modes as possible. The building it up from like static config and replicating it has advantages in that approach. The things that you lose, maybe we should go through each one of those and ask whether there's a Kubernetes equivalent that should exist. Or can you like map like some of the higher level Ray stuff? Because I think the other intuition would be in a serving configuration. The bigger your serving workload gets, the more important it is, the less likely that you need all that dynamic reconfiguration that Ray enables. And the higher the likelihood that you have controlled rollout. So that's kind of like, that's a hypothesis. I don't think we could like, you know, like intuitively, we expect that to kind of be true. But if that's not actually true from people running in Ray, we might actually want to correct some of our priors there. So that might be, can we get good feedback from folks? Like do an exercise of Ray serve feedback at scale from someone, whether that's you or whether that's others. Like that's a discussion I think, you know, we'd ideally like people to be able to have a consistent range of small inference workloads to very large inference workloads on Cube. Do people expect to run extremely large inference workloads in Ray? If they do, does it map to kind of how the kind of mindset that Abdullah is describing here, or does it map to a different mindset?
I want to mention here as well, like Jashin, like that's exactly the design philosophy behind this approach, which is like the exact issue that you mentioned here. Like you feel that you have a dependency on Ray, but I think with this leader worker set approach, you wouldn't care, right? Because whether or not they address that issue, you will still be able to deploy VLLM on distributed because like what you will end up with if you remove Ray, you will end up with the exact same thing, right? Like you have a group of pods that you maybe use PyTorch distributed library, right? Like to do the distributed computing or like the communication, or use Ray. It doesn't really matter in this design philosophy because we are not taking any dependency on Ray, whether it's auto scaling or communication or whatever, right? We're just deploying a bunch of pods, allow you to basically specify that there potentially there is a head or not. I think even if you remove Ray and use MPI, you'll need the same design pattern. So I think it was an advantage really from that perspective.
Okay, sounds good. Yeah, I think we can probably check offline on one or two like special case. Let's see, for example, like the disaggregation case. Let's see whether like middle work set can support it well. But I think in the meeting we have a limited time. Let's probably
we have a cap. I'll share it. We're discussing disaggregated serving in a cap.
Yeah, that's great. Yeah.
And Abdullah, is that microservice disaggregated or is that
no,
static?
it's within a static one. Yeah, but we can also use LWS with this like fully service based, because also we have those IDs that we enforced at the high level replica side. It should allow us to do fun stuff there.
Okay, cool. Okay, come back to the agenda. I think we finished the discussion on this one and the last one. We probably like to take some time to talk about the second one. We get some feedback from the community, like people like to host the model across different devices. I think especially when they don't have enough chips for the model. Let's say they have limited 880G. They probably like to use 840G or L40 to host the same model, and they can tolerate some like performance like downgrades. But now like Kubernetes, for example, like one deployment or one like leader working set, they mainly focused on the I would say like deployment focused on it doesn't it won't allow us to use different device for one single service, right? So that's a problem, like hosting single model across different devices or nodes, because most of the time I think the node won't have different devices. So the different devices here means different node. So for this one, do we think that's a orchestration problem, or we think Kubernetes can probably solve this problem in a native way, like yeah.
Abdullah and I have chatted about this. I think like I very much wanted to see what we could do about heterogeneous hardware. There's two reasons for it. Availability, I think like capacity availability is like a big thing. So if you can get Slack instances of a different type, that just means you have better overall reliability and you're willing to pay the complexity cost. Another one is that you can get different cost performance trade-offs, which I think will actually be a little bit more durable. However, that's operationally more complex. So if you can't, I think maybe like my answer would be, if we can't come up with something that makes it easier, then people won't do it because the operational cost, or fewer people will do it. If we can make it easier, conversely, more people will do it, because we're going to go through, every year or two, we're going to have new hardware generations. Google's dealt with this. Like XLA does. I think the internal Google mindset about this is a little bit different than GPUs, but there's some similarities. So like each generation adds new hardware capabilities, and JAX and some of the high level framework ecosystem, XLA compiles you down to the devices. And there's a little bit more of that philosophy in play. And then sometimes you want to be able to run workloads on older generations. It kind of the interesting thing, and I don't know if everybody else has seen this the same way, it seems like from here on out, accelerators are only going to get bigger and more powerful. But today's use cases, instead of like 7 billion models becoming less valuable in the future, I actually think we'll just see more sizes of model, where there'll be use cases where 7 billion is useful, use cases for 30, use cases for 100, probably use cases for 1 trillion. And in that scenario, I think heterogeneous hardware for a single workload, you'll have heterogeneous generations. You as an admin, to get efficiency, will want to bring those in. If you have to map a single workload to a single hardware type, I think you're going to have a lot of, a couple of years out, you're going to have a lot of matching problems, because you won't necessarily be able to use those as extensively. So all that being said, my gut would be, we need to think about what we do for multi-host specifically, gang scheduling, replacements. I think the easy simplification that Abdullah and I chatted about was, we don't worry about that inside a single replica. And then the next easy assumption would be, at least for today, you need something that helps you deal with the operational consequences of the different hardware performance characteristics, both memory size and the latency reaction to amount of traffic.
Yep.
So I think I would argue, if we have those primitives, then it becomes easier to do it on a per replica basis. But if we don't have those primitives, I suspect people aren't going to get there, but people can emulate it just by creating 2 deployments and having the different hardware. So I guess I would probably say I'm interested in solving that problem, but it's not the top priority one. Because I think, as Abdullah has pointed out to me multiple times, you can achieve it today if you need to. You just set up multiple deployments, you scale them differently, and you have to handle it at your traffic service layer, any differences. I don't know, does that match anybody else's, like, do other people have experience that says differently?
I mean, it does match. I know we've talked about this before, but like, it's not just also about different types of hardware. It's also about different provisioning modes, like going into spot right? Like fallback from like reservation to on-demand to spot, and being able to handle that operationally right now is a nightmare, especially when things change, right? Like, for example, you get more spot capacity and you want to give, like, downscale your on-demand ones and go into your like the spot ones so that you reduce your cost. That is something not like specific to serving here, but it actually related to the problem we were trying to solve with which exact replica you want to downscale, right? Like if you want to downscale the replicas that are on the most expensive devices or provisioning mode, right now it's random, right? Like you need to use, again, multiple deployments, and you need to have control over all of them, orchestration on top of them to do that. I don't think we have anything like this right now out of the box. You need to be creative with your metrics and whatnot.
Anybody, other folks have other opinions? Like I'm jotting stuff down. I think I would also note that CPU workloads have this problem today. Like, Carpenter has, prioritization classes. We see similar use cases and patterns in Google customers or GKE customers. I think a lot of people think about different classes of hardware, but they're typically thinking of priority, and most of the time their workload is guaranteed to work on the different classes of hardware. I think we want to keep that property for whatever we do, which is how do we ensure that a workload can guarantee that the hardware it gets, it's going to work on if the user is flexible. So that's like minimum constraints, DRA. Like I was reviewing the DRA stuff, and there's some examples of, it's kind of a lot of work today to go specify, I support all of these accelerators types, even in the current DRA proposal. I wanted to see if we could improve that. Like, can we say, A100 plus? And there's some reasons not to do that, but that's an example. So I'll jot some of these notes down. So
I wonder if anybody has like concrete examples on this. Like, Jason, do you have it in terms of like, do you, for example, try to use A100 and drop to some like lower end GPU? What is the exact use case that you, and what model sizes do you face this with?
I think so in this case, model size is not a big concern. So the major problem comes from the resource fragmentation. So sometimes let's say one model we have some devices available from another model setups, but currently this model have a high pressure. So technically we can leverage those resources for better throughput at the service level. But now due to their different devices and there's no primitives to allocate the servers on that kind of the resources. So technically, I'm thinking that's a resource fragmentation issue. So if we can hide those details, for example, let's say based on the GPU performance, we have some abstraction like just like training we use the flops like concepts. Then we can hide the abstraction on the GPU hardware side. So that's becomes I think that's another that's a problem, and there's another problem for very large context models. We actually used different context models to orchestrate the entire service. For some of the services, for some of the prompt, we know we don't need that long context model. Then we put it into for example, convert the request from the 32K to 4K context window model. So for those cases, we need different deployment as well. So
that one is a use case that other people have mentioned. I've seen that happen a couple of times. So I think that's one that we should just put on our list of, this is something that we'll see, because the different model sizes, at least today, you have to train a model to a specific size, and I don't see that changing in the near term. So, so you mentioned something about fragmentation. I was going to add density. Like these are big workloads. You run a lot of them if you're, leading edge. And because you're running a lot of them, you're probably running out of space. And then if you have more than one type of workload or more than one type of model that's competing for those same large hardware, the prioritization and preemption has to be thought of. So that's something today that that the current primitives don't make easy. Like you can set up preemption, but if you're keeping your clusters homogeneous in terms of hardware, you actually might benefit by being able to scavenge lower quality. And I think like that gets into like some of the operational challenges is you're going to have more slack capacity the older generation is kind of like a truism I've kind of assumed is like, every new generation is going to come out. A lot of people will use it for training. You'll have some leading edge inference stuff, and then you'll have a whole bunch of the older hardware. If the workload can run on the older hardware,
right,
there are operational advantages to being able to leverage it. So I do think we'll see use cases like that. I might actually put that as one of the use cases justifying heterogeneous. And so it's not as often about the older hardware stealing newer hardware, although that could happen. I think it's the other way around. Like the biggest workloads are going to want to pull the small stuff. Other thoughts? Anybody else have strong preferences on any of these or similar use cases for heterogeneous hardware? Beyond, is there anything from K-serve that you can think of? Multi-host or not, single host is, I think like some of these scenarios also apply for single host problems as well.
Yeah, I think probably let's use the last 5 minutes to talk about this one. I think in the multi node inference, like people need some scheduling support on the network topology aware scheduling, and sometimes to better understand the GPU topology, they need some like support as well. So I'm trying to see any further like requirements on this one. I think that's two known issues. I can give some examples like the inference side. Most of the frameworks right now they use the tensor parallelism, so it's better to leverage the NVLink to do the all reduced. So that's like the performance like a critical setup. And I think TPU have some like slicing features yeah, those tools I think are something I think critical to the model node inference performance. But like the disaggregation part, like how KB cache is transferred from the prefill machine to the decoding machine is another example. So to me, I feel those are like known like problems, and we need to address that at the scheduling part. But anything else? Does anyone have further like suggestions or requirements?
So I do think we've captured requirements for this in the DRA working group.
Oh, great.
And the use cases that we've generated requirements for are primarily around what would be within a single replica using Abdullah's terminology, even for multi-host. I think there is then what your scenario you've described. I don't actually think we've drawn out that use case. I think we should. Abdullah, maybe like, I don't know if Sergey is on.
I added a comment on John's document use cases. We're talking about like slices of a larger pod. And by pod here, I mean like a hardware pod. This existing TPUs will probably come to GPUs soon.
Yep. and I mean, I think that that's very logical. So yeah, so the first use case is multi-replica single host or multi-host single replica. Then it's between parts of a front end and a back end side that are probably part of they're part of two different sets of replicas, whether that's a single service or not. And then there's the third use case that I'm aware of, which would probably be the lowest priority. And John has been, we've discussed this with John, which is a workload can come along later. So something that doesn't require gang scheduling, so that you can schedule like caches or accelerators for the workload. So like the example I have, and this has been discussed in a few places, is you have a server that starts up that's on your NVLink domain, and it accelerates model loading by reading a model once from disk, and then when other instances start, they can ask that. You can do that within the workload, but one of the advantages is if you want to cache multiple types of content, like you want to cache models, maybe you want to cache multiple models because there's a small and a large model, or maybe you want to cache LoRa adapters. Being able to transfer those over NVLink in some cases, if you have a set of things that are rapid. Now, generally, I would say right now, memory is too valuable for this. So then other things would be like request caches. So you want to cache contexts and then share them. That's another one. So that's the third one. We probably haven't written down all the details. If anybody else has any use cases, I think the action item here is we should make sure that these are in the DRA designs for the networking scheduling part, and then we need to have a follow-up discussion.
Great. Cool. Okay, sounds good. Yeah, I think we're almost time, and yeah, thank you for attending the discussion. I think after the meeting, we can share the meeting recordings in the group channel, and people can use it for follow-ups. Yeah. Thank you.
Thanks.